Okay, good afternoon, everyone. In the last class or in the last few classes, we were looking into the EK dispersion, right? And then in the last class, we have considered nearly free electrons in weakly periodic potential. And just by considering that there will be gap opening at the Brougham zone boundaries, we got this kind of curve, okay? And then we mapped them within the into the first Brougham zone, okay? And if you keep and if you continue that process, then essentially you get this kind of EK dispersion, which we derived before in the chronic penny model. So this was the intuitive understanding that if electrons are uh, in weakly periodic potential, we also get similar kind of EK dispersion. Okay, then we move forward and we have seen how to find, like, okay, we have this EK relation. What is the essence implication? Why we are doing it? Okay, so it turns out to be that if we know the EK relation, then by taking the derivative, okay, we can get the group velocity. The group velocity is very essential, and with few algebraic steps, we could derive some sort of semi-classical equation of motion. Okay, and there we can get this following expression where force can be written in terms of a constant and times dv dt. It is like Newton's law for electrons, okay, inside the crystal. So this is like semi-classical transport. All the quantum mechanical phenomena is hidden here, okay, with here and here, okay, with the group velocity of electrons and with this EK dispersion relation, okay. So now the thing is, I mean, okay, we considered very simple chronic penny model. It can be anyway. We'll continue on that. Okay, so this was one of the things. Okay, yeah. So then we considered some toy examples. For example, we can always approximately write the expression of E in terms of k square proportional to k square near the band edge. Okay, conduction band, valence band, and in the Brougham zone. Then we have looked at, we have taken the dE by dk. We have seen how dA by dk varies, meaning group velocity varies. Okay, so here in this region we have parabolic approximation. That's why I have highlighted this. This is a simple derivative. Okay, and in between we can have some variation. Okay, if you know the functional form of it, then it is very simple. You can just take a derivative and get it. Okay, yeah. So that is the group velocity. This is how the group velocity is changing. So important thing here, already you notice that the group velocity strongly k dependent. That was point number one, and also it changes the sign. Okay, the green one is for the conduction band electrons, and this orange color curve is for the valence band electrons. The sign of the group velocity also changes, okay, for conduction and valence band electrons, which is important to note. Okay, now if I take one more derivative, then this is proportional to the effective mass. Okay, so if you take further, I mean, one more derivative, so this is constant, it will become, sorry, this is a slope straight line, it will become constant, and the sign of this constant, okay, meaning, so 1 by this term is effective mass, sign of this actually changing, okay, for electron, I mean, for electrons in conduction band and electrons in valence band. So this is very important. And so yeah, and in between there are some functional forms. Okay, if you know what is the variation here, and if you know the proper function of E, you can get that. Okay, so now if we have two extrema in between, okay, if the curvature is changing in between, there can be somewhere we can have linear dispersion. Dispersion meaning E versus K. One of the example is graphene. Okay, then I ask this question, in this case, what is the effective mass? Okay, do you think it would be infinity or something else? Okay, so here it is evident that if you take a derivative, first derivative, the velocity is constant. Okay, that is known as Fermi velocity. Okay, think about again, maybe we can discuss later. And also the notes I'm writing, I have written, okay, things in detail. Okay, yeah, you should check it out. Okay, that's very important because graphene is very important and interesting material. You will come across such linear dispersion again and again. Okay. Okay, so now, I mean, physically, we try to understand what do you mean by this negative group velocity or negative effective mass. Okay, so the physical significance, so that is related to holes. Okay, yeah, so at 0 Kelvin this was a structure, a band diagram, meaning the valence band is completely filled. Okay, what do you mean by that? So we have electrons in silicon or maybe some material, all are participating in bonding. Okay, everything is bonded. Okay, so there is no extra electron. But as you increase the temperature, electrons get kinetic energy. Okay, and then they are excited from the valence band top to the conduction band bottom. Okay, something like this kind of procedure happens. Okay, okay, this is what you get. This is the excited state. So that's why at room temperature or elevated temperature you get curve like that. But here still you won't have current. The reason is that you have equal number of electrons with plus k and minus k. They will cancel like this. Okay, so that is important. Okay, then what to do? Like how to get current? You need to apply electric field, bias voltage. Then what happens? Okay, so here before that I try to show what does it mean. So it means that we have those bonds, some of the bonds are breaking, so electrons got free. So this is a free electron, it doesn't care, it can roam around here and there, meaning it is in conduction band quite free. Okay, and so as this electron moves, so we have a hole, okay, or a vacancy of electrons, okay, as referred to as holes. Okay, now so this electron is free, this is an independent electron, it can go roam around here and there, but these holes now, okay, it is created there, but it is not that all the time you will have hole there, because from the adjacent bonds one electron can always hop. Okay, and if say this electron is hopping from here to there, the hole will come from here to there. That means a holes flow opposite to the direction of the electric field. Okay, so that's why in the here instead of tracking all electrons in conduction band, so we can also track holes, the gap. That will give us same information, right? Because the hole is nothing but the absence of electrons. But in that case, you need to flip the sign of the charge. Okay, that means you need to assume that, or you need to consider hole has same charge of electron. Okay, so same charge of electron. Okay, yeah. So this is, yeah.
Said that in second figure there is no current.
There is no current. Correct.
But what about the some electrons and holes are then present?
Holes are present at t equals to 0. They are frozen. They are just there. They are not moving. They are like statue. Okay.
This is for t equal to 0.
This is for t equals to 0. If t not equals to 0, okay, let me just clarify it. So the probability that this electron will go plus direction, it has the same probability that it will go minus direction. Okay, that means it will cancel. It can move, we can have lattice vibration, but overall the motion will be cancelled. Meaning, okay, so here it is more evident here. So we have plus k and minus k. Okay, if we have plus k and minus k, in principle electrons can move, but plus k and minus k state will always cancel. That means there is no resultant current, or there is no resultant flow of electrons. Okay. Okay, now, so to get the current, what you have to do, you need to apply external electric field. Okay, so suppose here we have applied external electric field along plus x direction. Then what will happen? This entire thing, whatever created here, will be shifted. This entire structure will be shifted towards x direction, towards minus k direction, and then you will get this kind of, okay, case. Now it is already evident that you have imbalance, okay, of carriers, imbalance in terms of momentum k. That means you have some number of carriers with effectively non-zero momentum or velocity. Shifting. This entire thing is shifted. No, you are applying electric field, right? If you apply electric field, what happens? It moves, right? It acquires momentum. That is also happening here. Okay, entire thing is shifted. Okay, so if I apply electric field along x, it is shifted. So electric field, electron goes other way. Yeah.
So we are applying electric field.
Allah.
In the green line, we are seeing the electron moving towards left.
Ah.
So in the red line, the hole should move towards right.
Okay, I really wanted this question. Yeah, so actually, let me just thanks for this question. Actually, what is happening now? Don't consider this electron. Okay, so what I'm saying is that the entire thing is shifted towards left. That means so whatever electron you had here will be shifted here. Do you agree? Do you agree? Now is it okay? Yeah, okay. Now, so note this point is same as this point. This is like extended Brougham zone. This point is same as that point. So instead of showing here, you flip it back, you get this. Very good point. Okay. Okay. I intentionally didn't clarify it. I just wanted this question. Okay. Make sense? Okay. So now we can define the expression of current. This is very basic. So rho is like total charge. It might have a distribution, right? Charge times velocity. Okay. Now you have seen that velocity also function of k. So you need to integrate. So in a sophisticated form here, actually what matters is the uh, 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 this asymmetry. Okay. So whatever electrons we have here in this section, they are symmetric, right? Do you agree? Here and here, they are symmetric, so they will cancel. So symmetric distribution, we don't care. That's why here we have considered delta F. Delta F corresponds to this thing. Okay, whatever asymmetry you create by perturbing, meaning by applying electric field. Okay, that will contribute to the current. So you need this distribution, this times charge, you can assume that is like total charge. Okay, and then velocity you need to integrate. That's all. Whatever we did, right? And if this is for one band, there can be many bands. We are generalizing the expression. There can be many bands, I number of bands. If there are many bands, you also sum for all the bands. Okay? Is it fine? Okay. By the way, so this was the recap, okay, from the last class. Okay, if you have more doubts, we can also take the questions later, okay, after class. Okay, so now today's class begin. So previously we have seen, now at least I hope you understand, I mean, you get the point why EK diagram is important, okay, because if you know the EK diagram, essentially you can get the group velocity, effective mass, and you can find the expression of current, provided you also get some other things, okay, that we'll get. But right now the point is, so we have uh, you got a flavor for 1D chain, right? We need to understand silicon, which are 3D. So our idea is from 1D to we'll go 2D and then 3D. Okay. So this is a simple 1D, okay, dispersion that we derived. Now consider this kind of rectangular, very simple 2D rectangular crystal. Okay. So this is a real space. Okay, how would a reciprocal space look like? You got 20 seconds. How will you know? You can do the calculation, but it should be, huh?
Like the AX would be small.
Yeah, so this is, yeah, so here, right, that's the answer, inverted rectangle, because the reciprocal vector is pi by a. So if a is longer, then this will be smaller. Okay, inverted rectangle. Anyway, you can work out. Okay, but that's what you'll have. Just this is extension of this. So if you have one chain, okay, now if you have more chains, then I think it's evident. Okay, fine. Now let's assume that we have this kind of similar dispersion, E proportional to k square. Okay, then how will you draw EK, E versus K? Now it is 2D. How many, like, so here it was simple, we have only one direction, right, X. Now it is in 2D. How many directions do you need to consider? In 2D plane, there can be infinite, right? But at least, I mean, you need to, I mean, have the minimum number of bases, right? So two important direction meaning along X and along Y. Okay, something like this. overall structure will be whatever we got. So along X, it might look like this. I'm saying might, okay. Along Y, it might look like that. But hope you understand that it will be parabolic, right? So why height is, okay? Is it clear? That will be parabolic. Secondly, do you understand this gap along X? So pi by A is smaller than pi by B, right? Because A is greater than B, right? Okay, now why this height is different and how? So that depends on the technical details, okay? I'll give some assignment problems so that you think about it, okay? And you can do it. But anyway, suppose this is given, okay? But now, okay, one thing to note, plus k and minus k, the bands are symmetric. We want to make things concise. Plus k and minus k bands are symmetric, right? Do you agree or not? Okay. So that means if I only keep this information plus k here, plus kx, I just drop this information because it is irrelevant, because they are symmetric. And I plot, I mean, along minus horizontal axis ky. Do you have all the information? Whatever, instead of showing two plots, this one plot is enough. Do you agree or not? Because whatever you have along plus kx, same happens. So why to keep that information? Right? You have studied the information theory in signals and systems. Okay. Yeah. So we are encoding it in this way. Right? Okay. So now we know what is happening x and y direction, which is fine. I mean, this makes sense because we have crystal symmetries like that. But what will happen any other random direction? Okay, for that, so there are two representations. So essentially now, okay, let me just explain it, okay. So suppose we are plotting E energy along Z axis, okay, and in X and Y axis we are plotting Kx and Ky, so 3D plot. Do you think it will look like that? Some sort of parabolic cup? Okay, this is just one of the cuts, okay. So when we are having E versus Kx, this is one of the cuts. So if I have a plane, so whatever you get, that has been shown here. Okay, if I take cut along Y, we get this. So you can take infinite number of cuts, meaning you can just rotate this, okay, right? Then you will get some sort of parabolic cup. Okay, this is the 3D. In Z axis we have electric field X and Y. This is in X and Y we have momentum. Okay, is this clear? This is what it looked like in 3D. Okay, but sometimes, so now it is for the 2D system. For 2D system it is becoming 3D. So but we are mostly interested in silicon germanium, that is 3D. Things will become much more complicated. Okay, so there are two things. One is that when we have EK diagram, we plot EK for we'll show also we plot EK energy cuts along certain crystallographic directions. Here we have done X and Y, and alongside, why don't you plot the constant energy surface?
You have the same circle, like same radius for, so but there the lanes are different.
That's a good point. Okay, so I will give, okay, I'll answer that. Okay, but before that, let me just wrap it up. Okay, yeah. So let's get the constant energy surface. Okay, so I'll just slice it. We have that parabolic cup. We just slice it for a given value of E. Okay, and that might look like this. Okay, so now if I have this information, E versus K along some critical directions, important direction, and if you have this constant surface, more or less you are okay. You have all the information. Now his question is like, I mean, whether this is circle, ellipse, right? That's the question. That's very important. So it is, I mean, it's tempting to say it will be like elliptical, right? Because X and Y things are length are different, but think about the height. Okay, so yeah, I mean, it can be elliptical, it can be circular, depends on their values A and B. Okay, yeah, so what I will give you in assignment problem, we just assume free energy, I mean free electron like energy, and then you will solve. So anyway, I just give you small hints. So here what happens, K is large, that is true, but look at this height. This height is proportional to K square. Okay, but here K is small, but height is small. So altogether, for this part, with this particular assumption, it will look like circle, but in general not, which we'll just see next. Okay, but this is a nice exercise. I'll give either in the project, mini project, or mini project will be uploaded soon, or in the homework problem. Okay, okay. So overall, what is the essence of this slide? That means 1D to 2D understanding. You need to visualize, and this is the most simplest structure. Okay, rectangular intentionally I chose. The reason is that if it is square, we'll eventually get circle. But what happens for rectangle with different assumptions, that is interesting. Okay, so hopefully you got this point, right? How to read band diagram, that's important. E versus K. Okay, and have the constant Fermi contour, or sorry, constant energy contour. Ready for 3D, or you need more time to understand what is happening here? We are just extending our idea 1D to 2D.
These things.
Which things?
That why the KY and KX, how to club together here.
Here.
No, this extreme right.
Here.
Yeah.
No. So from you just take this information from here to there. I'm just plotting 0 to pi by a here, and I'm plotting 0 to pi by b here. That's all. I'm just keeping this information here to here. I'm just keeping this information here to here. I'm just dropping this term, this part. The reason is that they're symmetric. Why to store your memory with this information? Okay. This is important because it will be evident. Okay. Now let's move to 3D. Okay. Our target, I mean, we want silicon, to understand silicon, germanium, gallium arsenide. Okay. One thing is that hope you remember from the crystal structure, these are FCC. Okay. Do you remember that or not? They are FCC? Yes. Diamond, meaning you have two interpenetrating FCC lattice, meaning you have two atoms per lattice. Okay. Two basis system. If you remember, if you don't remember, you should, I mean, play with the crystal structure. Diamond you cannot forget because our whole thing is on that. Okay. But overall the unit cell is FCC with basis, right? Do you agree or not? And previously we have discussed, if I take Fourier transform of FCC, meaning real space to reciprocal space, it becomes BCC. So you are already familiar with this. Okay. So the momentum space will look like that. Okay. If you don't remember, recap the previous concept. Also, we have lectures uploaded. If you by chance forget, just go back. Okay. But okay, assume that it looks like that. Okay. I think we have spent enough time. Okay. Explaining this. Okay. So now we need to, so this is the Brougham zone. Okay. But we need to plot E versus K. How? How to plot E versus K? Again, there are two things. We need to have E versus K along certain critical directions. You can consider n number of critical directions, but at least which are extremely essential. That's point number one. Point number two, constant energy contour. Now I can't say surface. The reason is that it will be volume. So constant energy contour. Is it okay? Okay. So which are those two important, or which are those important directions? One is the gamma point. Gamma point means K equals to 0. K2 X. Right, because this structure you see in this K space, this structure repeats. Okay, and another structure you have this hexagon, right? So gamma point to L. So these points are defined by the group theory. Don't worry about these names Y L, Y X, Y gamma. They are
This 3D is of constant energy.
Here. There is no, this Brougham zone doesn't need to be constant energy. You compare what happened in 2D. So that's the Brougham zone. Doesn't need to be constant. Okay. Because in the just previous example, actually, since I'm recording, I can't go back. I mean, but if you remember that two bands were different, right? Intentionally, I did it. Okay. So that you don't get this point that at Brougham zone energy is constant. Can be, but doesn't need to be. Okay, otherwise life is very easy if it is constant. Okay, Okay, but two critical directions are these, so we need to plot along this direction. Just the way we did gamma to x, kx, we'll also do gamma to x direction, right? This is important, and it will turn out to be like that. How? We don't care right now. The reason is that you need to do DFT calculation or time binding model beyond the scope of this. So now you need to take it for granted that these people have, physicists and material scientists have already found. Okay, but at least you know how to do it with 1D chain. For 2D and 3D, there can be more complications, which we don't need to worry. But important thing is that as an electrical engineer, you need to read the band structure and interpret and find important information. If someone gives you the band structure, you need to get all the information. Okay. So now you can read this. So this corresponds to valence band. This corresponds to conduction band. But that's not the full story. So we have also another important direction. So gamma to L. Okay. Fine. So it just looks like that. Okay. Now what are the things you read? This is important. Okay. Rest of this course. So now slowly, so we'll have a little bit more on, not I mean semi-classical thing like density of states. Maybe after this class things will be much more simplified. Okay. But you need to understand certain things. For example, EK diagram and okay, extract the parameters. Okay. Okay. Now let's try to read this. Okay. So these are like valence bands. Now you have more branches. Obvious, right? It is much more complicated structure. You will have many different energy levels. Okay. Okay. So now, okay, but one thing just for your information that what happens. So there are different bands. So there are some degenerate bands, meaning here two bands having same energy, at least near k equals to 0. And one of the band is split. So we call it heavy hole, light hole, heavy hole, and split off. Split off happens because of the spin orbit interaction. Whenever we have degeneracy lifted, we'll not get into that. Maybe people having higher physics background can appreciate it. But anyway, okay, we can have degenerate bands, non-degenerate bands, but that's what you have. Okay. Okay. Now important thing, conduction band. Okay. So where we have, okay, let's focus on this. This is gallium arsenide. So here we have the valence band top. Okay. So now this is a conduction band bottom. Okay, this is the lowest energy level here in the conduction band. This is the highest energy level in the valence band. They are aligning. Okay, if that is the case, then we call it direct bandgap semiconductor. Previously, whatever we have been sketching, that was for the direct bandgap semiconductor. Okay, this we call direct because we can have direct transition. Okay, is this clear? But now if you look at silicon and germanium, so this is the minimum of the conduction band, right? There are also other extremas, but this is too far. So this is the minimum. Do you agree or not? For germanium, they are close by, but this is the lowest one. Do you agree? So if any transition happens, so it must happen. So energy levels you have to think about. It must happen from here to there. It must happen from here to there. Okay, but they are not aligning. Now hope you understand, right? What do you mean by transition? So there is energy barrier, the barrier we called EG, band gap. I can give energy, thermal energy, meaning I can just raise the temperature. Okay, actually the quantized form of that is known phonon. Phonon, lattice vibration. Okay, so if you provide thermal energy, electrons can jump from here to here. If you provide this more than that, okay, and here it has to go from here to here. So instead of that, you can give light, okay, photons. Okay, so what happens? Photons carry very less momentum. Why? At least that you should understand, right? Why? Altogether, m is very small. Okay. So classically no m, but quantumically the rest mass is very small. So photons carry very small momentum. So here, note that. So when you consider the transition for indirect, so these are called indirect bandgap semiconductors. Okay, here, okay. So transition are indirect. The reason is not only you have to increase the E, you also need shift in K. electrons need enough momentum transfer. Okay, if you shine with light, only light, that's not possible. The reason is that you don't have enough momentum from light or photons. How you can work? We'll give some exercise problem. Okay, you can work it out. So that's why you need phonons. So this is always phonon assisted process. That's why indirect. So reverse thing is also possible, meaning if you have electrons here, it can fall. And in that case, for gallium arsenide, it is direct. You can get emission of photons. That depends on the band gap, right? E.g. is h bar omega. But here, you won't get it. The reason is you need much more momentum shift transfer. So mostly you will have phonon. Things will be heated up. That's why silicon germanium, they are not good. They are very good for electronics, but they are not good for optics, optoelectronic devices. For optoelectronic devices, we need materials like direct bandgap semiconductor, gallium arsenide. And importantly, if you dope with something, now remember in the first class we said there are also alloys. We can have gallium arsenide, we can have gallium nitride, we can have indium gallium. As you can dope with something, you can alloy. With all these mechanisms, essentially you can tune this bandgap. Okay, so whenever you tune this bandgap, what happens? The radiated energy is different. Energy meaning the frequency, which means the wavelength. That means depending on the band gap, you will have different types of light. Okay, suppose you want different types of LEDs. So this is like, okay, we'll get into that later. But you can have different wavelength of emission. You can have red, green. Recently, Japanese researchers got Nobel Prize for the green LED. Sorry, blue LED. Okay, but once you have red, green, blue, you can actually combine them and have all the colors. That's why now LED TVs, LED monitors are there, right? Okay, yeah. Any question here? One part is done. Okay, we are plotting E versus K along certain important crystallographic directions. Yeah, so here what is happening? Okay, look at silicon and germanium. So you need a transition, right? This transition is this valence band maxima to conduction band minima. So they are not aligning. So it is happening at different location. That means, so even if you pump energy, that doesn't guarantee that you will have transition because you need the momentum transfer to electron. Otherwise, so if this is K equal to 0, gamma point, here it is something else. So now how do you provide that? For that, you need to have phonons because phonons carry much more momentum than photons. Okay, then only is possible for, and that means the lattice vibration. Okay, and that's why you won't get light in the reverse process here. Silicon germanium is not good for optoelectronics, but excellent for electronics.
From the outside.
Right, right. So there are actually two: direct effect and indirect effect. Direct effect is if you are supplying phonon externally, meaning if you are heating up the system, you can have transition. That's what you have, right? That's what we have discussed, like bonds are breaking, doing this and doing that. That means this is a direct process. You apply phonons, you get this transition because that means you apply energy in the previous. Okay, you apply energy and also momentum. Okay. Reverse process is, suppose you have one electron here. If it falls, then what will happen? You will have phonon released. Okay, not photons, because you don't have that K shift. Okay, you don't have. Okay, is it clear?
Then we all actually means implicitly the x-axis is momentum axis.
Okay. Right. Yeah. I mean, this means like, yeah. By default, this is K and this is E. Now there are different points. Yeah, no, you can always write K. You can always write K. So for Pn, that is X. We'll get into that later. So that is at a first. Okay, first, yeah. Okay. So this is dispersion, energy dispersion. We'll get into that whenever we discuss. Yeah. Yeah, this x-axis is momentum. Actually, since I'm recording, I cannot go back. If you remember for the rectangular thing, we had kx and ky. We put that in the horizontal, on the horizontal axis. So here we are having gamma to x direction, gamma to L direction for this case. Several curves representing different bands. The reason is a real system. You have many bands. Okay, these are some of the bands within this energy level. Within this energy level, the deeper you go, lower you go, so you will be probing core bands. Okay, but we as transport or electronics or electrical people mostly deal something near the Fermi energy level. We will define it soon, near this conduction. So within whatever happening in this region, okay, within plus minus 1 electron volt. Okay, we don't care what is happening here because you cannot pump too much energy, okay, here to here. That's why you don't worry. Okay, so this is one side. Second part is remaining. That is the constant energy contour, right? Okay, so now the system is 3D. So when it was 2D, it was much easy to visualize because in z-axis we could have E and we can have x and y axis for momentum, right? Because it is 2D. But here that is itself 3D, like we have x and y. Okay, but anyway, so here it will be much more complicated. It just might not be too intuitive, but anyway, let's see. Okay. Okay, so this is what it will look like. Okay, these are the energy contour. So energy contour meaning we consider constant energy. Okay, so here we will consider constant energy near the band extrema, because again whatever happening very high, I mean above, we don't care, because you can have constant energy surfaces at different positions, right? Okay, so you think it in this way for gallium arsenide. Okay, it was direct band gap. Okay, so constant energy will be like symmetric around gamma point because it is direct. It is clear? That should not be that difficult. It is like 3D version of circle. If you have a square lattice, okay, you get a circle. If I make a cube, you get a sphere. Something like that for the gallium arsenide. But silicon and germanium, so this is the silicon. Okay, so in which direction you have energy minima, conduction band energy minima? Gamma x direction, meaning 100 direction. Okay, this is 100. So now, okay, again one point. So in real space, x is translated to this gamma x point. Okay, so we had real space 100 direction is translated to this gamma x. Okay, so it is happening somewhere here, not at the boundary, right? Not at the Brillouin zone boundary, somewhere close to that point. Okay, that's why it looks like that. So whatever you will see here, you will also have same copies because of this. So you have one, again you have another here, another here. Okay, how many of them do you have? So 1, 2, 3, 4, 5, 6, right? So you will have 6 constant energy contour. And it will look like elliptical because, I mean, x and other y and z doesn't need to be same. How the details is like hidden in the proper calculation, but doesn't need to be same, right? If it is not same, then it will be like elliptical.
Individual lobe, then that whole surface is constant energy.
Yes, absolutely. So here one constant energy. So within this sphere, you can imagine infinite number of spheres. Okay, all will represent, yeah, constant energy. Same here.
This momentum space, that one.
Yes. So this is like kx, ky, or maybe here kx, ky, kz. So with sphere, we are representing energy because it's a 4D plot. We have 3 momentum and 1 energy. If it is a 4D plot, either you make color plot, right? Or, okay. Now for germanium. So here I have not shown, but if you remember, it was happening at the Brillouin zone boundary. But but yes, but along ills, this is for the for germanium actually. This is for germanium and this is for silicon. So it is happening along this direction, right? Ill. How many ill directions do you have? 8. All the corners of this football sort of thing. Okay, that's why we are having ellipse here, 8 ellipse. Okay, what is the advantage of this? Because essentially in the end, what you need E versus K. Okay, so if it is a disk, okay, or circle, or I mean 2D ellipse, some constant energy is say a kx square plus b ky square. You get that type of expression. So here, so you will get this type of expression. You have A, B, and C. Now for gallium arsenide, A, B, C both are same. Okay, because this is isotropic. But for silicon and germanium, they are different because it is like ellipsoid. That's what turns out to be the case. Okay. Yeah, one important thing. Okay, so now, so in general, so we have different directions, right? So we were defining effective mass in this way. Okay. So, but now here it is like a tensor. It is a tensor because you have different directions. Along different directions, your effective mass will be different. Okay, and this is how to find. There is like tensor because you have 3 cross 3. You have 3 k values, right? I mean kx, ky are 3 important k directions. For 3 important k directions, so we are plotting only 2. Okay, but you can have the important 3 k directions, and for that we can have 9 elements. Okay, 3 cross 3 matrices, and this is how you can find similar to what you have. So we have d squared E by dk square, right? Now if we have cross terms, then it will be dk I dk j, and I and j can be ax y. Okay, so diagonal terms are d e square divided by dk x square, or d e square by dk y square, but we have off diagonal terms. So off diagonal terms will be represented like that. Okay, so it is very complicated, but you expected it, right? This is a real silicon 3D system. I mean, it will not be very simple. But the point is, if you understand 1D and 2D well, you can at least convince yourself, okay, how it looks like in 3D, how to deal 3D system. Okay, so I mean, so if you, I mean, you can derive it, but that derivation is, I mean, beyond the scope, right? You need to do DFT calculation for that. But the thing is, if I give this, okay, information, then you should be able to find this information. Okay. Okay. One last point here on effective mass, that anyway, I keep repeating that choice of axis, okay, is for our convenience. Right, we conveniently choose our axis system. That's why we have different types of axes, right? Cylindrical, then spherical. Okay, so now in silicon, this is very important. What I am saying, these are very important. In silicon, note that these ellipsoids are oriented along these directions, what we call x. So these directions also represent like Fourier transform of x, y, and z. Okay, so now, I mean, if you want to do, yeah, that's what it is. Okay, so now along this direction, we have this type of ellipsoid, and we can write. So here, instead of writing kx and ky, we are writing k1, k2, k3. Okay, suppose k1 is along this for silicon. So this is one of the ellipsoid, long axis of the ellipsoid. K2 and K3 perpendicular to those, because it is convenient to define it in that way. Then only you can write the expression in that form. And whenever you write the expression in that form, you know what to do next. Okay, you can find taking derivative group velocity, this, that. Okay, but this is our convenient way of representation. For silicon, it's fine, is expected. But for germanium, now we use our axis, so this K1, K2, rather than saying kx, ky, because x, y, z is this definition. But now we are defining k1, k2. So k1 you can assume that along the long axis of the ellipse. You need 3 axes, right, to define volume. So k1 is the long axis of the ellipse. K2 and k3 perpendicular to those. What I try to mean, so these are 3 perpendicular axes, right? Kx, ky, kz. But here, for silicon, we don't take it because high symmetric directions are happening along 111 point, where you have the conduction band minima. This is important. We are interested near conduction band minima. So let's define the k-axis along these. If you define k-axis along one of these diagonal directions, other 2 are easy, just 2 perpendicular to these. Is it okay? Is it okay? Or do I need to repeat? I previously told that things are not, it will take some time. Okay, so yeah, you have to think also later, also now, as much as you can understand. But one thing, do you get that you need 3 axes? This is a 3D system, right? You need 3 axes. So here in this scheme, this was kx, ky, kz. You always need 3 axes, right? Now when we are defining this constant energy contour, again we need 3 axes. We can take this kx, ky, kz. That's fine. That is working well for silicon. Because along, okay, now what is this kx or ky, but along this direction, so this is say kx is say k1, and then perpendicular to these are ky and kz, okay, that we say k2 and k3, which are the perpendicular. Do you understand? We have ellipse, one of the axis is along the long direction, other 2 are perpendicular to it. Simple. And that is aligning exactly here. This k1, k2, k3 is kx, ky, kz here. Next difficult version is for germanium, because now the long axis is diagonal. You can always write equation in terms of kx, ky, kz, but you will make your life more complicated, because it is very difficult to define ellipse with a random axis, right? Best is define ellipsoid. Best is define one of the axis along the long and have other axis perpendicular to it. That's all. First one. If first one is say along 1 k1, so other 2 k2 and k3, so that they are perpendicular. That's all. Okay. I think we try to put some tutorial or homework problems so that you solve, because you need to spend a bit more time in understanding. Okay, I try to include most of the information in my extended notes, but anyway, you need to read, comprehend, think, visualize, okay, solve problems, okay, then the understanding would be complete. Okay, so this is more or less, and with this we are closing this chapter of E versus K. Okay, okay, so what is our goal in general? We need to find current, right? Current conductivity. For that we needed to know Ek. Okay. So previously I said there was something called distribution. Now the question is, okay, let me just, before that small information, that the energy gap, okay, has weak dependence on temperature. For example, here 0 to 600 Kelvin, huge temperature change. Okay, so people have seen slight variation. For silicon, say it is varying 1.18 to probably 1. Small variation, less than 10%. Because when you change by default, what it means, when you change the temperature, okay, unless the system is undergoing transformation, you are essentially not deforming the system. Okay, you are not deforming the system, but overall there can be small changes. What is the origin of that small change? As temperature increases, the energy bands get broader. And if it gets broader, suppose we have 2 bands here, right? Okay, we have 2 bands. If it is broadened, then they will be closer. If they are closer, then band gap automatically decreases. There is no like mathematical analytical form of it. So people have done experiment and they came up with this kind of expression, okay, by fitting. Okay, just for your reference, but at least you need to understand that overall band gap, general trend is band gap decreases because of the energy level broadening. Is it clear? That's important. If you have bands like that, if it is broadened, they will be smeared out and come relatively close. Okay. Okay. So this is what we have seen. So yeah, now so these are the band representation, right? E versus K we had. So we call this is band 1, band 2, band 3 and so on. So now the point is, so bands are, what do you mean by bands? They are a collection of states, right? The states are so dense within a band that you cannot distinguish them. But there are states, many states. Now the question, what is the distribution? Do you think whatever states we have at this point, okay, exactly where I'm locating. So do you think the states will be same here? We don't know. That's what we'll derive. That means number of states per unit, okay, energy. Of course, per unit volume, you need to normalize, okay. That is called density of states. Next, we need to know the density of states. Why? Because where electrons will reside, that depends on the density of states, right? It is like chairs. These chairs are density of states. And you guys are electrons. Okay, so how many electrons, meaning students, are present? How do you find? There is a probability. I can roughly guess that out of 66, 40 are here. Some probability. Maybe I can have 40 today, I can have 50. Okay, there is some probability that you will come for the class. So meaning electron will occupy. It doesn't mean that it will, but there is a probability that electron will occupy some energy state. We need to know that. That is defined by the Fermi-Dirac stat. Okay, now in general, so what is the total number of electrons? It depends on two things. Suppose electrons, you have probability for finding electrons, but you don't have any states. Will you have any electrons there? You don't have, right? You are applying for a job, but there is no post vacant for that. How brilliant you are, you will not get the job because there is no post for you. You must have that density of states, right? Yes. So that is this density of states, and when you essentially, that means when you need to multiply these two things, right? Probability and density of states. So multiplying at one single energy value doesn't make sense. This is a continuous band. So you need to do this process for the entire energy, meaning you need to integrate it, right? If you do it, then you get the number, carrier number. Okay, fine. Okay, that means next. Okay, so carrier number you need to know. You need to know how many carriers are there moving with the velocity, right? So now velocity part you already understand that part from the EK diagram. But the number, how many, we need to know. Yeah. E1 I'm just saying, suppose this is our band of interest. We just start from here. Let this run to infinity. That we are not interested because when we say here, that's important question. It is electron meaning what type of electron? There, if I take silicon, there can be many electrons, right? Here we are interested mostly the electrons which will participate in transport, which is around the conduction and valence bands. Okay, we will suitably choose E as per our convenience. So the top one doesn't matter. The reason is that this function anyway becomes 0, so it will be 0. Okay, and wherever you have density of states available, you will have that integration, integrated value there. Otherwise, it will be 0. That's not an issue. Okay. Okay, that means what do we need to learn next? We need to find density of states. Okay. Yeah. Okay. So this is the definition of density of states. Not that difficult. Density of states meaning number of states per energy. Okay, but you need to normalize with the volume of the material, right? Because if I only focus on the energy states, if my sample size is bigger, we'll have more states, of course, but that doesn't give you any information, right? So you normalize with a sample so that it is intrinsic material property. Is it okay? Okay. So dn by, okay, so dn by, so for a given system, you need to find dn by de. Okay. So we just wrote, can I write dn by dk and dk by, so this you understand, right? If it is a 3D, this is a 3D volume. Simple Lx, Ly, Lz. We need to find dn by dk. dn by dk and dk by de. Is it okay? We can write it in this way. Okay, so now we'll start taking approximation because our interest is near the band extrema where we can take parabolic approximation for most cases. Okay, this is that parabolic approximation. You can take a derivative dk by d by dk. Is it okay? You can do it. So this expression is common for all the systems. Okay, as long as it exhibits this type of dispersion. Simple math. Now only thing you need to find for this case. So we are interested in finding density of states in 3D, 2D, 1D. 3D meaning 3D cube, I mean silicon. So 2D meaning if it is thin to 2D, okay, and 1D as you understand, okay. But this dA by dk term is kind of constant. If it is 3D, then we'll have volume, and accordingly we need to find it. Okay. Okay, now the question is how to find that. How to find number of states per K. Okay, that actually you know from the periodic boundary condition. This is like Schrödinger equation, right? Oh, every time, everywhere you have seen this, and a block equation meaning this point is same as that point. So here, so K typically, I mean, this takes this from 2 pi by Lx. If I have Ly, Lz, this equation you have seen many times, right? True or false? Okay, now we have n. What do you mean by n? If I have, so this n is integer, right? If I have n 1 1 1, that means this is a solution 1. We got one solution. We can have it 1 2 1, then it is a solution 2. So when we are having 1 2 1, okay, so this is like that. So that means we can have different solution, but as we increase the n in the k space, we are changing the volume kx, ky, kz. In that k space, also the solution will look like points 1 1 1, 1 1 2 in the k space like a grid. Okay, so can I say within this volume we will have only one solution, one state? Because if I have 1 1 1, if you take nx, ny, nz 1, then you get only one solution, right? That means within this volume you have one solution, meaning one state. This is important. That if you understand this, rest is very easy. Okay, so we should spend time here. Okay, this is a solution. Okay, so if you make n equals to 2, your size becomes bigger. So this is the smallest volume. So inside this smallest volume, you get one solution. That's all. That's what you need actually. That's what you need. So here we multiplied by 2 because each state can accommodate 2 spins. Okay, up and down. Or overall, okay. Okay, that means now conveniently choose some, because you need to take this derivative, right? Okay, so now let's take a sphere in momentum space because it is easy to take derivatives there. Okay, use our symmetries. Okay, let's take a sphere in K space. That means if I have somewhere. Okay, if this is a K space, okay, let's take this sphere of K. So what is the volume of this sphere? 4 by 3 pi k cube, simple, right? Okay, and now we agreed that within this volume we have not 1 2, okay, 1 or 2, okay, 2 states. So how many states do you have within this volume? Do you agree? Can I write it in this way? There is a volume of the sphere and this is the volume per solution. So this is the net in number of solutions, meaning in number of states. Okay, next is simple. So now you get the expression n versus k, right? The question is very simple. If I take this sphere, how many solutions you have? So what I'm saying, within a small box, within this small box, we have small box of this volume, we have one. So how many such small boxes do we have here inside this sphere? This divided by this, so this 2 comes from the spin, that's okay. So now already you get N versus K relation. Next step is simple, you just take a differentiation, that's all. Okay, differentiation is easy. The understanding you should focus. Okay, so if you take the differentiation, you can take 1 by V. When you are taking 1 by V, this will go. So this is what you get. Okay, so this dN by dk we are deriving. Okay.
Why are we taking a sphere? Why are we taking a sphere?
Sphere, the reason is that taking differentiation, everything is simpler. Okay, in 3D, because of the spherical symmetry, it makes our life, you can take any arbitrary shape, the answer will not change. Okay, but conveniently, again, you can take your sphere. Okay, fine. Okay, now, so we know what is dN by dk, what is dk by dE. If I put these guys together, we get density of states in 3D. So finally, we get this celebrated expression. This is proportional to E. Right. Because you remember we have bands near the conduction and valence band edge. It is like parabolic and we are interested there for our transport. We don't care whatever things happening outside. Okay. The second thing is that if it is 3D, then you have to consider a 3D momentum space sphere. Simple question, how many states do you have? So within what I'm saying, within this small volume, we get only 2 states. Meaning we get one state where we can accommodate 2 electrons. Then just simply this divide by that. That's all. Now you can take the derivative, you can get it. Okay? Yeah.
Like the different values of
Yeah. So if you make it 2, 3, suppose you take it 2, then within this volume 2 pi by Lx 2 times 2 pi by Ly 2 pi by Lz has 2 solutions. One is 1, 1, 1 and one is 1, 2, 1. That means this is a unit volume. This unit volume has 1. If you change any of them, then your solution will increase. So this is easy for us, right? This is a total volume we need. We need to know how many solutions we have. So better is just to know what is the minimum volume for per one solution. Then you know how many, right? Again, if you are not comfortable, you should read notes and then other books. Okay, I'll post. I have written all these. Okay, maybe figures are not there, but I mean you'll be able to understand. Okay, now our next job, maybe your next job, your job would be finding same thing for 2D. That is simpler. Okay. So this is what it should be. Okay. So dk by d well known. Just you need to find dn by d. How will you do it? Try solving. Yes. Otherwise you will be bored because 1D will not solve, that you will solve. Anyway, you'll find the solution in my notes. First thing is that what is the area? What is the area? LXLY, right? Area is LXLY. That's the most simplest thing. So what is the like size you will take in 2D? In 3D we took? No, yeah. So one by one. Yeah, that's there. So in 3D we took sphere, right? We wanted to know within a sphere of k radius how many states you have. Now what is the question? What you need to know? Within disk, within a disk of k radius, how many solutions you have? Okay. So how many solutions in general? What is the smallest volume for 2D in k space? 2 pi by Lx, 2 pi by Ly. So within that volume, sorry, within that area, you got one solution. Okay, so how many states do you have? Meaning within this pi k square area, n is we define n is the number of states within pi k square area. So the area pi k square divided by, okay, that what we have, this is the smallest volume. Within this smallest volume we have 2 electrons, meaning one state, 2 electrons, right? So what is the area pi k square? Within pi k square, how many carriers do you have? This pi k square divided by this. Acha, here we must have a, I mean, okay, this is a slash typo. Okay, so now you can take a derivative. This is much simpler, right? If you take a derivative, you can get that. This is what you will get. That is very interesting. The reason is that this is energy independent. Okay, it doesn't depend on the energy. Okay, so 3D I have explained, 2D partly because you guys are doing, at least while you are doing, you thought something. Okay, that is important. Now 1D I keep it on you. You should be able to derive. Then what you have to consider, length. Same approach. That is much easier actually for 1D. Okay, it will look like that. Okay, for 0D, what do you mean by 0D? Dot, right? Where have you seen such dots? Single atom. Energy level is discrete. Delta function. Okay, so this is how it's varying, and this is just a plot of that. So 1D, 2D, 3D. Okay, so now you guys know what is the density of states. Okay, how to define density of states. Okay. Okay. So again, this I have been repeating again and again. So 3, 2, 1, because the more you solve, better you will understand. But eventually, back to the story, we should focus on silicon 3D materials. So generally near the band gap, so we can have, I mean, here what I try to show, in general, if you do a tight binding model or DFT, your density of states may look like that, crazy, but near the band edge, we can have the parabolic approximation. Sorry, we can have, I mean, okay, anyway, this is also parabolic. It depends in which side you plot. Okay, it will take this form. Okay, fine. Now, what is the last piece remaining? Distribution. That's all, right? Yeah, with this, what will happen? Actually, I understand today's class is quite condensed. But anyway, if lecture is recorded, you can, okay, go through it again. Okay, so that's the advantage. Also notes I'll provide. But if it is, if we can keep that pace, then we might not need to take that Saturday extra class. Okay, but anyway, we still have 5 minutes. Achha. So now we need to know the distribution. These are states. Okay. Yeah. So before that, simple exercise. So this kind of permutation combination, and what class did you learn permutation combination? 11, 12. Also in GATE some questions come, right? Meaning if you want probability, it is there. So there's a question. We have 4 boxes. We have 4 boxes. Here GI number of boxes. And 3 identical balls, all red. Okay, meaning indistinguishable in number of electrons. What are the ways, how many combinations, or what are the possible ways you can arrange? That's all. Sorry? Here? Yeah. This, yeah. How many ways? 4C3, right? That's all. That means you know already. So now imagine these are energy states for a given band EI. We might have different bands. Within a band, we can have different, okay? So now, so that's why this ith coming. So we can have this, right? That's what you are saying, okay? Now the question is, already you know the stat. I mean, already you know the probability, which is good. Now the thing is, what is the most probable distribution? Now, I think that fundamentals are there, you know. Now you need to find what is the most probable distribution. Yeah, I mean, suppose you are arranging it. Think it in this way. You are arranging, she is arranging, he is arranging. You guys will arrange different way, right? So what is the most probable one? Not that easy. One have to do that. We'll not get into that. So there are ways you can take log, you will take differentiate. I don't think this is not a physics class as such, but yes, there are ways you can find the most probable distribution from these. Starting point is fine. Next is mathematical tricks. Okay, you can skip for the time being, or if you're super interested, you can go through the books. I have not included that in my notes. Okay, yeah. So, but there are some criteria of conservation because total particles are same. Okay, this is the total, and total energy is also constant. So here for electron, there is another thing slightly different from the ball. So here this is a one box, right? Imagine we have racks. In one rack we have say G1 number of boxes, another rack we have G2 number of boxes, another rack we have G3 number of boxes. Now it is a 2D sort of problem. All racks are different bands. Within a rack, how many boxes you have? That means that is analogous to the number of states within a band. So that's why you need to integrate, okay? But anyway, eventually if you do it, I mean if you do the process, then you will get some distribution, and then you have to find the coefficients using kinetic theory, thermodynamics. Eventually that derivation is, I really don't think that is really important, but how is arising, starting point you need to know, okay? Yeah, then this is the final distribution as given by Fermi-Dirac. This is what it is. Okay? So as an electrical engineer, you need to remember it. Okay? So now you have this distribution. Then what will you do? You just need to plot and try to see. So what are the things it depends? This distribution depends on the temperature. Does it make sense or not? Because previously try to connect to the intuitive picture. As we increase the temperature, electrons jump. So it has higher probability to go in higher energy states. That energy should come. Is it evident? That's evident, right? So it's fine. And some coefficient, some constant term comes known as the Fermi energy level, which is the critical. In the next, all the classes you will find Fermi energy level coming again and again. Okay? So you need to understand that. That's all. We'll wrap it up in 5 minutes. Okay? Not more than that. Okay? So at t equals to 0, what will it look like? So this one. The blue or the purple one. Okay, and so this is simple math. Okay, put t equals to 0. If t equals to 0, this term will be infinite if e is greater than some constant, right? If this is infinite, if e is 0, that's what it is. And this term, if e is less than 0, then it is e to the power minus infinity. That means this term is 0, you get the 1. So it is a step function. Okay, so have you, I mean, maybe you can already connect this to what we had at 0 Kelvin. So all electrons were in the valence band. That's what it is stating. Even if you have density of states, you can't have electrons in the higher energy level. It will be residing in the valence band only. Or if it is metal, electrons will fill up to some energy level known as Fermi energy level. If it is metal, we have free electrons, then you can compare it like water tank. Fermi energy level is the level, water level. So later on when we discuss, when we cover p-n junction diodes, we'll see that we'll have 2 water tanks with different water levels. Then what will you do? If you connect them, water levels will align. And these are the things you will see later that align that Fermi energy level, that is the starting point. Fermi energy level should be aligned. Okay, anyway, we'll get into that, but that's a flavor. Okay, now if you increase the temperature, what happens? If you increase the temperature, you can plot it will be slightly smeared out, meaning the transition will not be sharp. So here you have lower probability is slightly lower than 1, and here you have slightly higher probability. What does it mean? Meaning that electrons now will be able to jump from the lower band to higher band. As you increase the temperature, that process will be much more significant. Making sense? So this Fermi-Dirac stat makes sense, right? Okay, so now you have all the resources. You know EK diagram. You know how to read, interpret EK diagram. You know now what are the things to extract from EK diagram: group velocity, effective mass. And right now you have derived density of states, Fermi energy level. Essentially, fundamentals are kind of done. Next time onward, so we will use them, okay, and use semi-classical transport. Quantum mechanics part will be gone superficially, okay? Okay, that will continue in the next class. Before that, very quickly, two curiosity questions. Suppose here, so now here, okay, I gave this option that, constraint that each box, I forgot to tell, each box can contain only one ball. This is the distribution for that. That means this is a Pauli exclusion principle. In a energy level, you can have only one, okay, or electrons to two spins, which is the multiplication factor. Now, if this box can have any number of balls, what would be the possibility? Huh? Derive it. Derive it. Okay, and that leads to Bose-Einstein standards. Okay, that leads to Bose-Einstein standards. Meaning photons can. Anyway, you do it and okay, and yeah, finally you will see something. Now another thing is, now here in both cases particles are indistinguishable, meaning all are red balls. Suppose one is red, one is green, one is purple. That means if you have distinguishable particle, anyway, you can derive, that will lead to Maxwell-Boltzmann equation. So these are the three pillars in StatMech. No matter what you do, so all stats should belong one of these three statistics. And based on that, there are three fundamental types of particle: boson, electrons, and the distinguishable particle. Those are like gas molecules. Okay. Very recently, another new type of thing emerging that typically happens in quantum material systems. Anyway, we'll not get into that in this course. But Majorana fermions, those follow a different stat. Yeah. But anyway, so this literally wraps up the fundamentals. Okay, you'll probably not see a Schrodinger equation anymore in this course. Okay.